Dear participants, I introduce myself. My name is Charlie Laneluc. I am a power electronics engineer working at CIE Grenoble in France and also coordinator of Modulity project I'm going to present. This project gathers 9 European partners, and this project has received a funding from the European Union of 7 million euros. Modulity aims at developing a new generation of modular electric powertrain for battery electric vehicle up to full-scale demonstration integrated in a battery electric vehicle platform. During the project, the consortium has developed an innovative modular powertrain using new technologies. It is mainly composed of the following elements: the battery, which is not part of the powertrain and located often on the floor of the car, an inverter using wide-bandgap gallium nitride semiconductor technology, a high-speed buried permanent magnet machine with an optimized cooling circuit, cooling both inverter and electric machine, an innovative high-speed transmission and brake gearbox connected to the wheels to make the adaptation of the speed between the electric machine rotor and wheels. Finally, an innovative regenerative braking strategy to recuperate the mechanical energy available during freewheeling and send back to the battery. The powertrain of the future must be reliable, efficient, compact, modular, with a low carbon footprint, and of course, low cost. Reduce manufacturing costs and raw material supplies, improve the reliability, the integration, and the modularity, along with an increase of the efficiency and good regenerative braking strategy are the objectives of Modulity. The following slides will present the main achievements of the project. First, the design of a high-speed multi-phase electric machine, then the GaN-based inverter, the optimized transmission and cooling system, the module assembly and conditioning, and finally, the expected and potential impacts of the project. Concerning the high-speed electric machine, the high-speed electric machine converts the electrical energy into mechanical. Brusa, a company building drives based in Switzerland, has designed a 6-phases high-speed buried permanent magnet motor. The maximum speed of the electric machine reaches 23,000 RPM, twice the speed of the BMW E3 electric machine speed. The speed increase has some advantages, such as less rare earth magnet, minus 50% as comparable e-motors, higher power density, higher efficiency, lower active weight. Efficiency on test bench has been measured, and the electrical machine efficiency reaches 97.4% max at 6,000 RPM. High efficiency on only several operating points is not sufficient. It has to be efficient in a large band of torque and speed. The efficiency is also high in a large band of torque and speed from 4,000 to 14,000 RPM and from 10 to 160 Newton meter. The e-motor develops a very high efficiency, high peak power over a wide speed range, a sinusoidal back EMF, low torque ripple, and a good overload capability and very good cost potential due to low active weight and magnet mass reduction. The motor performance compared to Modulity objectives are reached, even exceeded, and region in the table achieves specifications. The motor with a peak power of 160 kilowatt reaches a power density close to 28 kilowatt per liter. The inverter is based on gallium nitride semiconductors technology, having unrivaled switching performances, low conduction losses, and no recovery losses. The use of wide-bandgap semiconductors will increase the inverter efficiency and also its integration using compact semiconductor devices. The Modulity inverter is powered by a battery and must power the electric machine requiring 225 amps RMS per phase. However, due to the lower current capability of latest GaN switches provided by GaN system compared to silicon carbide devices or silicon devices, the maximum current per phase has been decreased to 120 amps RMS, which corresponds to the continuous power of the electric machine. The topology used is not standard, as it uses full bridge configuration with serial bidirectional switches allowing to pass from a 6-phases machine to a 3-phases machine. It has the advantage to reduce the current per coil necessary to reach the high torque demand, increase the voltage per phase, but also to isolate failures more easily and have a better operational continuity. The controller here is developed by TU Eindhoven, based in Eindhoven. The inverter runs at this time at 90 ohms RMS. The maximum efficiency almost reached 99% at 25 kilowatts and 97% at 65 kilowatts. The main limitation seen here is directly linked to the improvement of the technology itself. Smaller dies lead to more difficult thermal management. This is why the requested current for high torque cannot be reached due to too high losses of switches at high currents because the heat is not extracted out of the device efficiently enough. Still, it is a world first today to use GaN semiconductor in an automotive inverter with such output power. Powertrain, which is an independent full system supplier of fuel-efficient powertrains in Belgium, has investigated and developed a dual ratio transmission for optimal performance in collaboration with ZG, a transmission specialist company. First, the transmission efficiency at such speeds is dependent of gear geometry and bearing configuration. They also mastered the lubrication system to accommodate motor, power, electronics, and transmission. Then, the cooling system has been optimized with the collaboration of IKA, a university with fields of research in energy and thermal management based in Germany. It cools down the power, electronics, and the motor. The cooling circuit design has been carefully studied to reduce load losses and also optimize the evacuation of waste heat by placing, for example, cooling fins on the cooling inverter side. Finally, they investigated the possibility of reuse the wasted heat to condition other components such as the battery or the passenger cabin temperature. Here are pictures of the powertrain on the left-hand side with all subsystems, e-motors, inverter, transmission, cooling, integrated with a cross-section view on the right-hand side. The power density reached with all subsystems integrated reaches 1.7 kilowatt per liter. Before the real assembly, a virtual assembly is made thanks to modeling softwares. Siemens, specialized in energy fields and modeling, models the integration of all subsystems altogether from partners, motor, inverter, gearbox, drive shaft, housing, tires, suspensions, chassis, battery, etc. Then the controllers, such as the innovative regenerative braking strategy from the Chalmers University in Sweden and shifting gear strategy. Cycles are applied to the virtual model to estimate the powertrain performance. Finally, the real parts are assembled all together. The testing cycles and procedure are defined. At this time of tests, an industrial inverter from Busa was used because the GaN inverter was not available on time. Modulid has opened research topics such as reliability of wide bandgap GaN semiconductor in automotive application, injected magnet, software algorithm for automotive application optimization, waste heat transfer, etc. From a market integration point of view, motor and transmission have a high level of maturity and technology readiness level and could be in the near future be integrated in the automotive market. However, the inverter using new gallium nitride semiconductor technology has still a lower TRL and high cost further away from a market integration. Modulid consortium covers the whole value chain of electric vehicle and hybrid electric vehicle markets. Thanks to the support of car manufacturers, the consortium will be able to demonstrate the relevance of the Modulid concept towards the market. By providing low-cost, efficient, and versatile powertrain, the Modulid is addressing the needs of the car manufacturers to be able to respect the CO2 emission regulations worldwide. On behalf of the consortium, I thank you very much, and I thank the European Commission for allowing me to present Modulid project. You will find my contact detail and also the website link of the project. Thank you very much.